I'd like to show you how to basically work out thermal systems problem, in particular a steam turbine analysis problem in MATLAB. So let's go ahead and get started. So here we go. I'm going to try to show you at least my version of the way that I've analyzed a steam turbine for a real honest-to-goodness problem that was frequently asked at my workplace. And so here is a frequently asked question, and I'll read it to you, asked by managers at my manufacturing workplace over the last years. Here's the question that I would get frequently from a manager. Determine the power that can be produced by a steam turbine with an available flow of 6 kilograms per second, with turbine inlet conditions of 3.1 MPa and 260 degrees C, a discharge pressure of 310 kPa, and a turbine efficiency of 75%. Oh, and that manager typically would say, I need that answer by lunchtime today. So it wasn't the type of thing where you'd go back and scratch your head and maybe work for weeks on it, get some guidance from others, ask someone else to do the problem. As a mechanical engineer, you should be able to answer this question pretty quickly. Now, why would my manager ask me this question? Production of power from a steam turbine. In my workplace, we had a large power plant that produced steam for a couple of purposes. One would be for process steam used in our manufacturing process, but also basically running a power plant because we also needed a significant amount of electric power, and we were able to produce that power much more inexpensively than the power company. We were also able to sell electric power to the power company whenever we could make excess electric generation. And so managers would ask me this question to find out what type of additional revenue could we make if we could produce power from steam that was produced extra by our boilers as a result of imbalanced demand of steam compared to what we're making from our boilers. And so this was a common problem or situation that we had, not a problem, a situation where we had excess superheated vapor steam produced, and we wanted to determine, rather than just condensing it and throwing it away, or not utilizing that heat, how could we send that superheated steam through a steam turbine, run a generator, make electric power, and then, of course, how much value would that be? Okay, so let's go about solving the problem and answering my manager's question before lunchtime. So let's, of course, start with a sketch and plan our work. And so here's my sketch of a steam turbine. Okay, inlet state 1, outlet state 2, fully insulated turbine. And here is our tried and true temperature entropy diagram depicting what the given information that we have: superheated vapor coming into the turbine, an adiabatic turbine. Now let's see, we know our turbine is adiabatic and irreversible, and we have the turbine efficiency, 75%. So we're going to draw two process lines. One would be this vertical isentropic line. That's going to enable us to get the isentropic work. Now we have the mass flow rate, so if we get the isentropic work, that also give us the isentropic power, and then we'll apply the definition of turbine efficiency, 75%, to get the actual power produced. And so here's going to be the irreversible and adiabatic process 1 to 2A. So anyway, that's going to be our sketch. Let's see, let's remind ourselves of our fundamentals: steady state, steady flow, open system, and there's a very generic open system, Q dot N. For our problem, it's going to be 0, adiabatic turbine. W dot out, that's what we're seeking. Let's see, continuity equation, the mass flow rate out exactly equals the mass flow rate in, of course. And here's a statement of our first law. And as engineers in operations, we're going to say, look, we're going to neglect any changes in kinetic energy of the steam, and we're certainly going to neglect or changes in potential energy of the steam is going to be zero anyway. So there's an interplay between the power produced and the enthalpy change. We'll study the isentropic process, 1 to 2i, determine W dot out isentropic, and then apply turbine efficiency 75% to get the actual output power, and we'll have the question answered, and we'll report back to our manager. Okay, let's see what we got. Okay, I think we've planned enough. Now, we haven't done this in we haven't done the sketching, we haven't done the planning in MATLAB, but here is going to be a screenshot of the beginning part of my MATLAB solution of this. So there's my key to go live. So let's see, I'm going to escape out of PowerPoint, minimize PowerPoint, and I'm going to go direct to MATLAB. Now, here's what I started with. All right, so solution. How would I go about solving this steam turbine analysis problem in MATLAB? I started with the file steamwaterfunctions.si. I hope you have watched the video on what's behind this generic situation, this generic MATLAB program where I've got a bunch of function calls available to me. Yeah, a lot of comments here. And then in this base file, steam water functions, do you see that I've just provided some demos, memory refreshers for myself and others that I've shared this with. How do you do this? How do you call the functions? So this is just my demo program. So what I did to solve our turbine problem, I just went to Save As, and I saved it to a new file name. Now, I've already done this, so I'm going to cancel my Save As here. Okay. And I saved it to a new file called Steam Turbine Power Demo. So let me close out my source MATLAB file. All right, so now I've just got one file loaded into MATLAB, Steam Turbine Power Demo. Okay, let me scroll up. Okay, and so you can see that I've saved some of the comments from my original file, but I've renamed it file Steam Turbine Power Demo. You can see I'm signing it. That's me. I did the work on October 5th. So I put the date on it. I put in the problem statement, typed that in from my manager. I discussed the approach. Determine the isentropic power, determine the outlet enthalpy. I'm going to have to determine the phase of state 2 because nobody's giving me any answers. I've got to determine the phase of state 2i first. I'm going to show you how to do that in MATLAB. And then once I've got the isentropic enthalpy, I can get the isentropic work and then apply the turbine efficiency to get the actual output power. All right, so here we go. So let's see. I use my usual MATLAB clears, and then I deleted all of those demo function calls, and here I've got solution. All right, we'll quickly browse through this. I've entered P1 and T1. So MATLAB variables P1 and T1 makes sense. Fat fingered in the numbers. And also on this one, do you see I'm saying what I've got with units? That's important. Comments in here. The next thing I'm going to do, look how easy this is getting properties at state 1. I'm just going to invent a variable named H1. Here's my function call, HPT. I know it's superheated vapor. H as a function of pressure and temperature. And look, there's my function call, and I'm putting in P1 and T1 as my inputs. That's the enthalpy of superheated vapor at the inlet. And also remember, I'm going to need the entropy because that's the way I'm going to study my reversible adiabatic process. S1, there's my function call, SPT, same idea. This stuff here is just preparing to write those results to verify what I've got to the command window. It helps me verify that I'm on track on my solution. Okay. Next thing I do, let's see, outlet pressure. I've got to determine my state 2i. I think about my sketch that I've got maybe written on pencil and paper over here to my right. Okay. Let's see. Determine the phase of state 2I. Let's see. S2I equals S1. I just looked up S1. So S2 isentropic equals S1. Okay. Now, let's see. The next thing I would do would be I would go to my pressure table. Oh, here I am. I've got to define my P2, 310, kPa. Okay. So I'm going to call for SG2. That's the entropy of saturated vapor at state 2. Look how easy this is. SGP. SG of P, and there's my input, P2. So I've got a number for S2I. Okay. S2I is S1, and I've got to compare that to SG2. If S2I is less than SG2, then my phase is a saturated mixture. If S2I is greater than SG2, then my phase at state 2 is superheated vapor. And I would have to use different function calls depending on the phase. So here's the next part of my solution. Determine the phase of state 2I. Okay. So I'm going to use a MATLAB if then else setup. If S2I, it's a number, is less than or equal to SG2, both of those are numbers. If S2I is less than SG2, then I'm going to create a new variable called phase equals text SAT, saturated. That's my key and I will display to the command window state 2I saturated mixture. Now, if it's not, if S2I is not less than or equal to SG2, then my phase must be superheated vapor. So my variable phase is SHV, and I'll display a different message to my command window. Okay, so at least now I've determined the phase of state 2I. Scroll down a little bit. So the next task then is to figure out let's see, H2I, depending on the phase, right? And so let's see, if my phase is superheated vapor, it's really pretty easy. I've got S2I and P2, and I would simply make my function call into the superheated function, superheated vapor function. Now, I'm expecting my phase to be a saturated mixture. So here I've created this. It says the else. So if it's not a superheated vapor, it must be saturated mixture. Wow, I've got to do a bunch of work to determine X2I. I've got to determine the quality at state 2I. Well, how will I do that? Let's see. I'm going to get the saturation temperature at P2. I just make a function call. T2 is, since it's saturated mixture, it's T sat P at the known P2. So now I've got, okay, great. I've got the temperature at state 2. Now I can use my function calls. I'm going to look up SF2 and SG2 using my function calls at T2. And I'm also going to look up HF2 and HG2 using my function calls since I've just found T2. So now all of a sudden, magically, I've got all of my needed saturation properties for my saturated mixture. So I can immediately solve for the quality at state 2I, X2I, definition of quality, S2I minus SF2 divided by quantity, SG2 minus SF2. Look how similar this is to a handwritten solution. I'm preparing to write out to the command window what's my numerical result, X2I. Okay. Now let's see. Okay, I've got the quality for the isentropic process. I can go now and get the enthalpy, H2I. I wish I could hold up my paper setup. Don't have that right now. Okay, H2I, simply using the definition of quality. X2I, just found that value, times HG2 plus whatever's left times HF2, the percent that's left, 1 minus X2I, HF2. Okay, so I've got H2I. H2I is determined. As you notice, I'm making a little note here. I'm working down the page, explaining my work as I go. Skip a few lines. Now I'm going to use the first law to determine the output power. What do I need to get the output power? I've got to enter the mass flow rate. I haven't written that out yet. So here it is. M dot equals 6, and I've got units, kilograms per second. So W dot isentropic, statement of the first law, simplified. I've got it in my head because I've planned my work. W dot isentropic is going to be M dot times H1 minus H2 isentropic. So I've got all these values, isentropic output power. Now I'm going to make a note in my command window to write the result. Isentropic output power is W dot isentropic. Okay. Now I'm going to apply the turbine efficiency for the actual output power. Wow. I've got to define my turbine efficiency. There it is, 75%. Making a little note in my MATLAB solution. W dot actual. See how my function, my variable name sort of makes sense. W dot A. W dot actual is turbine efficiency times W dot isentropic. And there it is. Look at that. I think I got my manager's answer in my solution. Here's I'm showing by comment end of solution. And I've just left in from my source file all of my function calls to remind me if I need to do more work. And then on and on and on are those built-in functions. I just leave those alone. Leave all of those alone. Ooh, wow. So let's run it. Let's run it. I'm going to move my Zoom menus here. And so I'm going to run it. I'm going to try running it. There we go. And it did run, thank goodness. Now, the first time through, I made a couple of mistakes. I had to go troubleshoot a little bit, but here's the finished product. Let's see what I'm providing to the command window so that, gosh, I could make a copy and paste, either a screenshot or something for my manager to communicate before lunchtime. Here's your result. Well, the result is the actual output power for that question is 1.9 megawatts or 1908 kilowatts. But notice here in my command window, I've got all my input data too, right? So I've planned ahead and I've written out the input data. So if the manager forgot the question, exactly what was the flow rate, what were the pressures, the pressures in question, those kind of things. That's just a reminder for everybody, both me and the manager. And so here's the bottom line: actual output power, 1.9 megawatts. And then we could turn that into cash money if we've got the value that we can sell electric power back to the power company too. So you get the idea. There is my steam turbine analysis in MATLAB. Okay, so the command window, just as a reprise, lots of comments here. Whoops. I've shown solution in comments. Notice here, I've selected variables that sort of make sense. I work down the page, of course. I'm careful to write out in comments the units of things, and I'm also trying to explain. I'm trying to explain what I'm doing as I'm going down the page. Determine the phase of state 2I, okay? Determine H2I depending on the phase. Remember, I had to use a MATLAB if, then, else arrangement because I could have a superheated phase, which I did not. I had a saturated mixture phase, which I did, and this is what was used in the solution. And then look at that, I'm explaining, use the first law, et cetera, et cetera. So really a screen, and that's it. And so basically a screenshot of this result. Should be enough for me to report back to my manager before lunchtime. Here's the result of what you asked me. Now let's see, let me minimize MATLAB and let me show you how to find the steam turbine analysis file. I'm going to go to my browser, and here I am at J's Toolbox, jstoolbox.vt.domains. Anyone can get to this. It's open to the public. I'm going to go to Toolbox, and I'm going to drop down my page, MATLAB. All of my MATLAB files that I offer are contained on this one page. So let's just start scrolling down to look for the steam turbine analysis file. Don't see it yet. Steam tables English. Here it is. Steam turbine demo MATLAB. Okay. So you can click this download button right here. Okay. That will immediately give you, you can possess the file you were just looking at in MATLAB. You can run it. It will run. Okay. And perhaps you could use it maybe to save as, to maybe solve one of your own problems. Now let's scroll up. Remember the one little detail. I've had to save all of my MATLAB files in the .doc file type. It was the only way I can post them out on my website. So you would open that file, the downloaded file in Notepad, and then you would save as file type .m to get it into the MATLAB ASCII format. Okay, so that's the way you can possess this file. Let's go back to PowerPoint. Okay, we've done the go live. Okay. Now here is the command window output. I've got to move my Zoom windows around so I can see the command window output. That's just the screenshot I took. This would answer your supervisor's question well before lunchtime. Okay. And you would send, I think, in a friendly, respectful email, for example, you would write some narrative information, not just, you would not write, please see the attached. You write some narrative information and perhaps include this screenshot along with your narrative information reporting. I've analyzed the steam turbine situation you described, and my estimate is that we can get 1.9 megawatts of electric power out of running this steam turbine driving a generator. Okay, I just showed you how to access this particular MATLAB file for you to save it, run it, have a look at it, see if you can use it as save as. Okay. So what's our recap here? I'm hoping that you're recognizing the power of save as. That's the way I started this. So I leveraged my own generic steam tables MATLAB file demo, and that was my starting point for creating the steam turbine analysis. Reminder that we did start with a sketch and a solution plan before we went into MATLAB. It's hopeless to go right from manager's question into MATLAB. You've got to start with a sketch. You've got to draw something down on pencil and paper. You have to have a solution plan in your head, and maybe have some pencil and paper work off to the side as you do your MATLAB solution. So document your work outside of MATLAB. That's the sketch and the plan. And inside MATLAB, use lots of MATLAB comments, starting with that %sign. And then, of course, my usual reminder, look, you've got to understand the fundamentals of how do you analyze a steam turbine? How do I access certain thermodynamic properties? What's the statement of the first law? What's the statement of the continuity equation? What are isentropic processes? You've got to have a pretty good handle on all of that before you undertake a MATLAB solution like this. Okay, I hope that gives you some ideas on how you could start using MATLAB in solving your own thermal, fluids, heat transfer problems. I'm going to come up with a few more, but I hope this gets you started.